In this segment, we'll talk about the direct method of interpolation, which is also called the Vandemonde method, and we will limit our discussion to linear interpolation. So if you look at the general order direct method of interpolation, you are basically given n plus 1 data points, let's suppose, or what we should say is that you are taking n plus 1 data points to do the interpolation. Because many times you'll be given more points, but you will choose only a certain specific number of points to do the interpolation. So if you have n plus 1 data points, what you can do is you can make a nth order polynomial to pass through these n plus 1 data points, and that's what is being denoted here in this picture here. And what we'll do is we will take it easy. We will only do the first order polynomial, or what we call as linear interpolation, in this segment. Let's talk about linear interpolation. So linear interpolation would also be called as straight line interpolation or first order polynomial interpolation. So they are the same names. So how linear interpolation works in order to be able to make sense of the data is that, hey, we are given x and y values only at 2 points. So let's suppose this is x naught comma y naught, and this is x1 comma y1. And what you are interested in is to find out the value of y at some value x, which is somewhere between x0 and x1, let's suppose. So one of the things which you might have already done in other classes is that you say, hey, let me go ahead and draw a straight line which goes between those two data points. So it does go pass through those two data points, and that's why it's called interpolation. So the bottom line becomes that, hey, if I'm able to find a0 and a1, then I can find the value of y at any point between x0 and y0, x0 and x1. So how do I find a0 and a1 is by saying that, hey, this particular straight line is going through this point and is going through this point. That sets up two equations, two unknowns. Hence, you'll be able to find out what the value of a0 and a1 is. Let's go and do this through an example. It'll be better illustrated that way. So in this example, we're asked to find the value of the velocity at t equal to 16 seconds when the upward velocity of a rocket is given at these 6 data points. And you can very well see that this velocity at 16 seconds is not one of the data points. So we have to somehow figure out how we can use interpolation to do that. We're also asked to use the direct method of interpolation, and also we're asked to use the first order polynomial. So as we have gathered that for the first order polynomial, we need 2 data points. So the question arises that which of these 6 data points will I choose? Which 2 of the data points will I choose out of these 6 to find the value of velocity at 16? So it makes perfect sense that we choose the 2 closest points, which are to 16, but they also should bracket the point of t equal to 16. So in this case, we have 15 and 20, which are the closest point to 16, but at the same time, they also bracket the value at t equal to 16. So basically what I'll be doing is I'll be choosing these 2 points in order to be able to find the value of the velocity at 16. So let's go ahead and do that and see how it goes. So we have v sub t equal to a naught plus a1t, and since we are using the values of the time at 15 and 20 to find what the velocity will be between 15 and 20, that will be the domain in which this particular first order polynomial will be valid. We already, let's rewrite, v sub 15 is already given to us as 362.78, and the value of the velocity at 20 is also given to us as 517.35. So let's go and use this information to be able to find a0 and a1, because the velocity at 15 is a0 plus a1 times 15, and that will be equal to 362.78. Similarly, the value of the velocity at 20 will be a0 plus a1 times 20, and that will be 517.35. So you can very well see these are 2 equations, 2 unknowns. That's how it gets set up. So let's write it in a cleaner fashion, we get this with coefficients in the front. And keep in mind this coefficient is 1, not 0. And then the next equation will be this one. And now we can set up this as 2 equations, 2 unknowns, and the matrix form, because we should be using numerical methods to solve our problems. So it's 1, 15, 1, 20 by using our matrix multiplication. And you get 362.78 here and 517.35. So all we have to do is to solve these 2 equations, 2 unknowns, to find A0 and A1. Let's also graphically look at this this particular problem. We have time here and velocity here. So what we have basically done is that we have 2 data points, 15, 362.78, and then we have another data point coordinate as follows. And all we are doing is we're drawing a straight line between these 2 data points, which is given by A0 plus A1t. So let's go and find out what A0 and A1 turn out to be. So we find A0 to be equal to minus 100.93, and A1 turns out to be 30.941. So our original expression, which was V sub t is equal to A0 plus A1t, and keep in mind this expression is valid only between 15 and 20. So we get this. So if I want to find the value of the velocity 16, all I have to do is to substitute the value of 16 into the straight line formula or the first order polynomial formula, and this is what I get. I get 393.7 meters per second. And that is the end of this segment.